question many science students have asked over the years. Why do we have to use significant figures? Why do they matter? Why are they so important? Well, we're going to aim to answer that in this video. But to do so, we first have to go back to a different concept, and that's the concept of accuracy versus the concept of precision. If we think about firing an object at a target, where the bullseye is the center and that's the point you want to hit, an accurate shot is one that gets close to the target. It's close to the true value of something. So if you're measuring something, an accurate result is one that's close to the true value. Let's say that you, for some reason, need to determine the density of a sample of aluminum. Now, we've known about aluminum for a long time. It's got a known and accepted density that's been measured repeatedly. The density of aluminum is 2.70 grams per cubic centimeter. Well, if you measure a sample of aluminum and you calculate a density for aluminum of 2.69 grams per cubic centimeter, that's pretty darn accurate. Woohoo! You got very close to the true value. Accuracy is really about being right. It's about getting the true value for something we know, or getting very close to it. Accuracy is getting the correct answer, getting close to the true value. Now, what if you measure the density of aluminum a couple of times? Well, what if you measure the density of aluminum 4 times, 4 different samples, and you get numbers like this? 2.69 grams per cubic centimeter. Darn, that's really good. 3.72 grams per cubic centimeter. 1.90 grams per cubic centimeter. Oh, 2.25 grams per cubic centimeter. Yikes! Now, if we already know the true value, we can look at these and say, oh, this result is accurate. Awesome, fantastic, yay, go me. These are all pretty questionable. They're pretty far off the true value. But what if we don't actually know the true value of something? What if we are attempting to calculate something for the first time? We have a different problem here. So our numbers in this set of measurements lack precision. Precision is the ability to replicate measurements again and again and again. So we said this set of measurements is not precise. One of them's accurate, 3 of them aren't, but they're really all over the board. A precise set of measurements would look like this. Now that is some precision measuring there. We happen to know that it's not very accurate, but the numbers are tightly clustered. Whoever made these measurements is able to make measurements with the same instruments that come out the same way every time. So these are very precise. Precision isn't about being close to the true value. Precision is about being able to make the measurements the same way and having the numbers come out clustered very closely together. Precision is not about being correct, it's about being repeatable. So that set of numbers we looked at here in the last thing, as we said, are very precise. But they're not close to the true value. They're not accurate. Now, in the best of both worlds, we managed to get a set of numbers that are both precise and accurate. This set of measurements is precise. The values are very close together. Now, it also is accurate. That's the gold standard. So to think about this in terms of the target that we looked at on the first page, this one is accurate. All of the shots are fairly close to the target, though they spread out in all different directions. This one is precise, but it's not accurate. The shots are all clustered together, the value has been obtained repeatedly, but it's way off from the actual mark. This one is both accurate and precise. This is really the standard. This is what you want to hit. All the values are clustered close together, all the hits are on the target, and they're close to the bullseye, so they're close to the actual value. Oh, sigh. Then there's this. Well, is it accurate? Sort of. Is it precise? Not really. Those values probably average to something that's near the true value, but they're so spread out it's hard to tell. And if you're not sure what the true value is, then you'd be guessing at what direction from those values your true value is. Not a good position to be in. What you're always aiming for is this, accuracy and precision. Now, what does this have to do with sig figs, Moser? Glad you asked. Whenever we make a measurement, the instrument that we're using to make the measurement has some kind of limitation. There is a smallest marking, and we can only estimate one digit beyond that smallest marking. We use sig figs to keep track of how precise the instrument was, what the smallest markings on the instrument were. So, if we look at an example of a ruler with 3 different sets of markings, you can see very clearly that one of these enables you to make a very vague sort of statement. If I'm measuring this object, I can only say, yeah, it's about a half of whatever these units are. My eyeballs aren't good enough to estimate that this is 0.45 meters. My eyeballs are good enough to say, yeah, it's about 0.5 meters. You can always go one digit more than the last thing marked on the slide, or on the instrument. Now, if I'm measuring that same object on here, I can say, oh, well, that is 0.50 meters, or 0.50 decimeters. Let's start over on this one. If we have 3 rulers with 3 different sets of markings, and the first one is only marked at the 1 meter length, if we attempt to measure an object like this, whatever it is, a piece of wood, a book, something, and we're measuring it on this first ruler, the best we can do is saying, well, there's the half. I don't know. Let's see. Maybe that's the half. So it's a little over half. It's not quite 1. Well, it's closer to a half. We can say that this is 0.5 meters. We can't, our eyeballs aren't good enough. Our eyeballs aren't good enough to say that that's 0.6 or 0.75. We can just go to the half or the whole. Well, if we're measuring this same object on the next ruler, oh, hey, we can definitely say that it is 0.7 meters, and we can estimate the difference between the 7 and the 8 to say that this is 0.7, I'll say it's about a half, 0.75 meters. Well, if we're measuring the same object and we use the last ruler that's shown, we can actually look at that and say, well, yeah, that's 0.7 meters, and it's on the 5, and it's exactly on the 5. So that's going to be 0.750 meters. Each one of those allows us to make measurements again and again and again with this tool that are more and more precise. And we keep track of the number of digits in our measurement to show the level of precision of the instrument. So, the big reason for using significant figures is to keep track of how precise our measurements are. When we're handed a set of numbers, we have to trust that whoever made those measurements kept good track of their significant figures and that the number of digits they hand you reflect the precision of the instrument. That means that when you're using the triple beam balances we keep here in the lab, if you have 3 and the other marker lies right there, that's going to be recorded as 3.312 3, and if it's spot on, you get a 0. Grams. That is how precise you can be with that balance. Now, if it was a little past that 3, we'll move this up. And it's hard to tell if it's sitting right between the 3 and the 4, like that. That's going to be 3.335 grams. Recording all the digits that you possibly can allows you to tell someone else how precise the instrument you were using was. We call this last one the uncertainty digit. And it's the one that you're estimating. It's one more than the last marking on the instrument. Okay, now you know why we use sig figs. You know a little bit about accuracy and precision. You can go on and watch the rules for sig figs video.